Hello. What we're going to move onward to is tackling conditional distributions in the case of jointly continuous random variables. Okay? This is section 6.5 from the textbook, Ross's textbook. Now, before we go into the details of this section, I wanted to remind you a little bit about PDFs of continuous random variables and looking at what the PDF is when this set A is tiny. So if f is the PDF of continuous random variable x, then you know that the integral over a of f of x is the probability x is in A. In fact, the way you find the probability x is in any set is you integrate the density over that set, okay? So you know this. Now suppose that the set A is a tiny set and it's like the interval from x to x plus dx, okay? And where you're thinking of dx as something small. Then what would be this probability? It would be the integral over a, in this case x to x plus dx, of the density. So ft dt, of course I can't use the letter x over here because x is used as part of the variables of the limit. And when dx is small, take a look, let's suppose that's a graph of the density. When dx is tiny, well, firstly, what is this integral? The integral is area under the density curve from x to x plus dx. The function's non-negative, so I can just talk about the area under the curve. And when dx is small, what will this area be? This area is approximately just the area of the rectangle that you can look at with height dx and with height f of x and width dx. So that's what this is. Okay, so, and that's true, of course, if dx is small, the area under the curve is going to be very close to the area of this rectangle. Okay, and this expression, when you have dx is small, gives you f of x times dx approximately. So suppose you were looking for, if you're looking for the probability x is in A, you could even go in that direction. Then what are you going to do? You can do a sum, suppose some set A is an interval, then you go take small little increments and take lots and lots of intervals, take small increments of length dx, and like basically partition the set A and add up all these probabilities. So you'll be summing that over all these small little partitions of A, and then take a limit as dx goes to 0, so that Riemann sum in the limit will be this integral. So anyway, in both directions, you know that is the probability that x is in A, and this is approximately, the probability x is in x to x plus dx is approximately the area of this, or f of x times dx. Okay, so that was just talking about some old stuff for continuous random variable, and that was from chapter 5. Okay, so now let's move on to 6.5. So suppose you have random variables x and y are jointly continuous. Okay, so the probability that x is in some interval x to x plus dx, given that y is in some interval y to y plus dy. Suppose you're looking at this conditional probability. That is E given F. This is an event E. Think of this as an event F. Then what will that be? You know from the conditional probability formula, that's the probability of E intersect F over the probability of F. So I wrote this down. So that's E intersect F over the probability of F. Okay, so this is the probability that X is in the interval X to X plus dx, Y is in the interval Y to Y plus dy. So I have drawn this line X and X plus dx, and here's y, and here's y plus dy. So you're asking the probability that the random variable x comma y is in this interval, in this rectangle, that is this probability in the numerator. Okay? And the probability x comma y is in this rectangle will be really given by the density, joint density over that rectangle. That's the true probability, correct? Now, since dx is tiny and dy is small, you think of dx and dy as small, then what will this be? Well, you could just take the value at x comma y and then multiply it by the area of the rectangle, right? So just take the value of the density f of xy at x comma y and multiply by this area, and that will be approximately this, which is this. Okay, so approximately f of xy dx dy. Oh, sorry, not that whole thing, just this numerator. And how about the denominator? We just saw from this kind of stuff that is approximately the PDF of y times dy, right? I just showed you this probability at random variables in this small interval is just given by the value of the PDF times the length of that interval, the value at one end times the length. Okay, so this is the PDF of y. I've written more below reminding you how to find that. Okay, and dy, these are just small lengths of the interval, and that is this length. You can cancel that. And once you cancel that, what do you end up with? F of xy dx over f sub y of y. Okay, so now I want you to look at the two ends. On one end, we don't even need the E, Y, F. On one end, you have this. Oh, I didn't copy it. And this, is approximately equal to this. Okay. All right. Now take a look at the right side. And why is this an approximation? This is an approximation because dx is small, dy was small, but not 0. And you can't do 0 over here because the function f of xy integrated over a point, that'll be 0, so you can't do that. But take a look at this equation right here. You can see that the right-hand side doesn't depend on dy, but the left-hand side does depend on dy. So what we can do is take a limit of the left side as dy goes to 0. So take a limit as dy goes to 0 over there. And if you have a limit as dy goes to 0, what will this turn into? This becomes y equals y when dy goes to 0. Okay, so that gives you the probability x is between x and x plus dx, given that y equals y, is given by this. So let me just move this, sorry. I will write that next. So you have the probability okay. So now you just think of this. This is a density. Think of this as a density. If you want even, you can even write the dx like this. Okay. Think of this as a density of the random variable x given y. Because you see, go up here, the random variable x has a density of f, and you have that the probability that x is in that interval is given by this times dx. So think of the random variable x given y, and you know the probability that x is in the interval x to x plus dx given y is given by this f of xy over f sub y of y times dx. Okay? So this is the reason to talk about all this is to show you the motivation behind defining the conditional density, probability density of x given y. The density of x given y, that's the random variable you're talking about right here. Okay? So the density of x given y, that's how you write it, dx, you'll define this to be this. So this ratio over here, let's put it in a box. This ratio over here is defined to be this. Okay? And that chatter was all to explain the motivation behind why the conditional probability density function of x given y equals y is defined to be f of xy over f sub y of y, and it's defined for all the little y's where the denominator is greater than 0. And if you compare this conditional density with the one that you had in the discrete case, you see it's exactly the same. You see? Over there we had f of xy, f sub y of y. Over here we have p of xy over p sub y of y. Okay? So this over here is the definition. All right? So mark it as one important fact. This is the conditional probability density function of x given that y is y, defined for all this. So that's the definition. Okay? All right. And just some more chatter. For small values of dx, this represents the conditional probability that x is between this given that y equals y, just like I had said. Okay? So, now suppose you want the event that x is in A given that y is in y, then what can you do? You can just use this conditional density and integrate it over A. So you think of this as a density of a random variable. Which random variable? The random variable x given y equals little y. Okay, so let me explain this with an example. Okay, so suppose you have that x is height of sun. Y is height of father. Okay? And maybe you can just put in at age 25. Okay? And you want to, now the father's born, he's in existence, he's past 25, and you want to find out, now that you know this father's height, what will be the distribution for the height for the son? Well, if you just look at the joint distribution of x and y, that will be this, okay? This is just the joint distribution of heights of sons, fathers overall, You can have the son's height on this axis, the father's height on this axis, and there's some density over here, okay? And of course, if you can think of the density as this two-dimensional function on x, y. And if you want to think about the height of it, you can think of it as like a blanket over this plane. Okay? So obviously this has some density. Now, what if you're looking at a father who's 6 feet 4 inches. So now what you're doing is you're restricting, let me move this a little bit. You're restricting your view to fathers who are 6 feet 4 inches. And now you're asking yourself, what is the density for the sun's height? Well, let's suppose this is 0. Of course, you don't have 0, so maybe it is kind of like normal, maybe not quite. Let's do this. Maybe it's something like this. You know? And maybe the mean, I think in general they say people's heights are increasing. So maybe the mean is 6 feet 4 inches, 4.5 inches, you know? You don't know. I mean, it could be something, you know. You don't know for sure, of course, what the sun's height could be. But this distribution, this function I've drawn over there, really, you know, it's, you really, I mean, what I mean to say is take this function and rotate it so it's coming out of the plane, you know, it's coming up from the plane. This iPad's plane, or sorry, this Surface plane, it's coming up from it. And for each value of y, you have a certain density for the height of the sun. Okay? And maybe the mean is just a little bit more than the father's height. Or it could be something completely different. Of course, that's not the only variable that comes into play. Okay? So maybe you could have some kind of a different distribution also. Okay? So anyway, that was just me trying to explain that if you given information about one of the variables, then it becomes like you're talking about what is the distribution of the random variable x given that y equals 6 feet 4 inches. Think of this as a random variable. Let's call it w. This is a random variable and it has a density. And that is the density for it. Okay, that is some function that depends on just one variable x. And of course, it would be different if you change this. Okay? All right. So, if we want probabilities of the event x is in A, given that y is y, then you use this conditional density and you integrate that over A. So if you ask the question, what's the probability that the sun's height is between 5 feet 5 inches and 5 feet 10 inches? Well, you integrate over that interval, this conditional density, where you've plugged in the father's height over there. Okay? And of course, you know, if you, why is that integral? You can think of it as like, here is this probability is approximately this. Now, if you make set x is in A, break up A into little small bits, subintervals, and then you'll be adding up these probabilities over that subintervals and take the limit as the length of the subinterval goes to 0. That summation, limit of Riemann sums, will turn into an integral, and this will be the probability x is in A. Okay? All right, so how do you find this? Like I said, it is this. How do you find the conditional density of x given y? X given y. So this, suppose you were talking about this example. You would write f of x given y, x given 6, 4. That's how you would have written it for this example that I just talked about. All right? Okay, so let's just put that a little bit low. Okay, so how do you find this? Well, you will take the joint density function and divide it by the density of y. What is this? This is the called the marginal density of y. This is the PDF of y. How do you get the PDF of y? Here is a small little description of how you get the PDF of y. It's a recap. Suppose you have that f sub y is the density of y. Then for any set A, you have that the probability y is in A comes from integrating the density of y. Okay? Now, let's put this in the scenario of y, not just the random variable y, but let's also talk about x simultaneously. So in that case, if you want the probability y is in A, what is it? That's the probability y is in A and x is anything. Okay, how do you find that probability? You take the joint density and integrate x over minus infinity to infinity because x can be anything and y in A. All right? So now let's look at this. This probability y is in A comes from this. Okay, I'm going to mark this in here. That is the function. When you integrate out the x, there'll just be a random, just be the variable y, as you know from Calc 3. That function, if you integrate for any set A, you integrate that function over A, you get the probability y is in A. But you also know that if you integrate the density over any set A, you get the probability y is in A. So this integral is the same as this, which is true for any set A. And that is a true fact. That is from calc, if you have that integral over A of g of x dx equals integral over A of f of x dx for any set A, then it must be that f of x equals g of x on the whole real line. Okay? So using that, you have that the density of y, this is given by this. Okay? And that was independent of what the value of y is. So for any y, you have that equals this. Okay? And similarly, on the x side, the density of x will be equal to the integral where you integrate out the y. And you know once again that these definitions, they're analogous to what you had in the discrete case. In the discrete case, how did you get the probability density, a probability mass function for y? What did you do? P sub y of y. If you fix any y, how did you find the probability? Y equals little y. You add it up over all the different values of x. So P sub y, if you want, let's just write this. One more thing, sorry, I should. Over here, we are talking about that's the probability mass function of y at 4. This is the probability y equals 4. X is anything, y is 4, and you just add up over all the different values of x. In our continuous situation, you integrate over all the different values of x. Okay? All right. So the main things to know are this conditional probability density formula, definition of conditional density of x given y equals y. That is a definition. Okay? And before we move on to an example, I do want to quickly just talk about the CDF of this random variable. So you have the random variable x given y equals y. This random variable, it's not two random variables, it's one random variable. What is the CDF? The conditional CDF of x given y equals y. It is a probability that x less than or equal to some value x given y equals y. So what would you do? Well, you just like you did, this is the density of this random variable. So you'll integrate over the set from minus infinity to x, the conditional density of the random variable x. Okay, so what did I do? I am talking about integrating that from negative infinity to x, but obviously I cannot put the letter x here because that's one of the limits of integration. Okay, so this is what you have, that the conditional CDF of x given y equals y is, and if you want, you write it as so normally what does a CDF mean? So now when you write it like this is the probability that x less than or equal to x given y equals y. Okay? Okay? So that's what you have. This is the conditional CDF of x given y equals y. All right, so like for example, in the son-father example, we could talk about what's the probability that the son's height is less than or equal to a certain value. We just take the joint CDF and plug in that value for x. Okay, the y is already there, whatever you had set your y to be. Okay. I mean, of course, you could think of this as a function of two variables, and you know, when y changes, this function would change too, but you're not thinking of it like that. You normally just think, okay, y is a certain value, and if y is that value, what is the behavior of the random variable x? Okay?